Hello, my name is Ania. Welcome to the lecture on battery management system functions, and thank you for joining me in the transition to sustainable energy. In this section, we'll discuss what a battery management system does, the things it measures, the decisions it makes, the calculations it performs, and the actions it takes. A BMS for lithium-ion cells must measure the cell voltages. For something really simple like an RC airplane, that might be enough. For good state estimation or for good safety responses, the BMS also needs to measure battery current and the temperature of the battery. Many BMSs incorporate a few additional measurements. Often, it is easy and useful to measure some temperatures on the PCB. For safety-critical systems such as electric vehicles, additional measurements are to diagnose the BMS itself, ensuring that the electronics are operating correctly. Based on these measurements, the BMS detects system safety events. Overly high voltage, current, or temperature can cause damage, and so should be prevented when possible. Additionally, large batteries, such as automotive batteries, typically implement diagnostics to detect BMS faults. The BMS is like a watchman. If your watchman falls asleep, or if your BMS isn't working, you cannot rely on the safety functions provided by either. A common goal for automotive batteries is detection of any single fault. Many small batteries, such as in your cell phone or electric skateboard, don't implement that level of diagnostic coverage. Many people think about state estimation algorithms when they say battery management, and would call state estimation the heart of a BMS. A BMS uses its measurements as inputs into algorithms that estimate state of charge and available power. In an electric car, the state of charge is directly related to the range estimate provided to the driver. The available power is a function of state of charge and temperature and cell health, and is typically electronically communicated to the motor controller or inverter or charger or whatever power electronics are charging or discharging the battery. The main action that a BMS can take is to open a battery switch. In a car, that high-power switch is a contactor. In lower current applications, it may be implemented with a relay or a transistor. Many BMSs communicate with the rest of the system. For example, the application may request the BMS to close the battery switch. Or, if the battery is nearly empty, the BMS may issue a warning that the battery will soon disconnect and allow the system outside the battery to power down gracefully. Or, if the battery is nearly full, the BMS should ask the charger to please stop charging. Lastly, a BMS can balance the cells, which is to say, if one cell's state of charge deviates from the rest, the BMS can bring it back into balance. In this lecture, we will look at each of these functions in more detail. Let's start with what the BMS measures. This schematic shows a typical battery architecture. We have some number of cells in series, 12 cells in this schematic, which is a typical number for a home energy storage system. 12 or 13 cells in series measure about 50 volts when fully charged, which is considered a fairly safe voltage. The regulatory requirements for 50-volt systems are much easier than for higher voltage systems. We for sure must monitor the cell voltages, and we need to measure all of them. If any cell becomes overvoltaged, it can be damaged, and many lithium chemistries can go exothermic, which is a fancy word that should have you thinking about smoke and fire. So, no cell, not even one, should be charged beyond the maximum voltage specified by the cell manufacturer. We also should monitor the battery current. High currents can damage cells, so we need to monitor the battery current to know when it's time to politely ask the charger to charge slower, or politely ask the motor not to exceed some load, or abruptly open a switch to disconnect the battery immediately. We'll talk about the switch later when we discuss BMS actions. A common way to measure battery current is to add a shunt, which is a resistor that has a small and precise value. Shunt values may be milliohms or fraction of milliohms. Why so small? We'll discuss the shunt value in the next slide. The maximum current that a cell can tolerate depends on the cell's temperature. Many cells should not be charged when the temperature is much below freezing, for example. So, we need cell temperature sensors. How many and where to place them is a matter of mechanical and thermal engineering. You will typically see one or a few temperature sensors in a battery pack. Why do you think we monitor every cell voltage, but only a few cell temperatures? In both cases, in normal operation, the measured values should be similar for all cells. The cell voltages should all move together as we charge or discharge. The cell temperatures should all move together as ambient temperature changes or as the battery heats up because we're pushing a lot of current through it. In an ideal battery, we could monitor only one cell because the rest would behave identically. So, what's non-ideal? What effects cause cell voltages to differ? What effects cause cell temperatures to differ? For cell voltages, self-discharge can change cell voltage. All cells have some internal leakage. This leakage depends on temperature. So if we have a temperature gradient across the battery pack, the warm cell will discharge more than the cool cell. This leakage is small, but over time can cause one cell to be at a lower state of charge and thus lower voltage than another. Capacity differences between cells can also lead to voltage differences. If we have a lower capacity cell, either due to a manufacturing difference or due to unequal aging, that lower capacity cell will reach empty sooner than a large capacity cell. We need to stop discharge when any cell is empty, so we need a voltage sensor on the lowest voltage cell. And since we cannot predict which cell will be the lowest, we need to measure the voltage of every cell. For temperatures, cells can get warmer than the rest of the battery pack due to proximity to other hot things. For example, if there's a bus bar that gets warm with high current flow, the cell closest to that bus bar may run warmer than the rest of the battery pack. The direction and path of the battery coolant can cause a temperature gradient, with the coolest cell near the inlet and the warmest cell near the outlet. Interestingly, though, we must measure every cell voltage, but it's okay to measure only some cell temperatures and model the rest. Can you tell what's different about the processes in the left and right columns of this table to justify this difference? The processes on the left aggregate. If a cell self-discharges more than the rest today, the consequent imbalance will still be in place tomorrow, and tomorrow's self-discharge will increase the imbalance further, and more the day after that. Temperature imbalances, in contrast, tend to reach steady state. For example, a coolant gradient tends to reach some designed maximum. Also, temperature gradients equalize on their own. If the battery has a temperature gradient consistent with the coolant flow, and then you park your electric car and let the battery rest, by the next day the battery will be close to isothermal. To summarize, a capacity difference can grow indefinitely, while temperature differences typically are self-limiting within some bound that engineers can characterize by testing and simulation, which allows us to model temperatures between temperature sensors. In discussing temperatures, we should mention thermal runaway. Do you think a BMS should monitor for exothermic behavior? What should the BMS or the system do in this situation? Let's look at what the BMS can see during an exothermic event. On this plot, we have time on the x-axis and cell temperature in orange and cell voltage in red. In the span of about 10 seconds, the temperature rises abruptly from 200 C to 600 C. The researchers used temperature to trigger thermal runaway. Other methods of initiating thermal runaway include overcharging or puncturing the cell and thus shorting the anode and cathode. However we start, the behavior is similar: a rise in temperature in a matter of seconds and an erratic voltage reading. Sometimes the voltage drop is on a much faster timescale than the temperature rise. Sometimes the voltage appears erratic before the cell becomes fully shorted. But in any case, 2 of our standard BMS sensors show measurable and dramatic behavior when thermal runaway occurs. Which should we use? This data was collected with a thermocouple on the experimental cell. In practice, most BMSs use thermistors, and the circuit is designed for a minus 40 C to 125 C temperature range, or possibly even narrower. Also, with only a few thermistors within a large battery pack, if the cell that enters thermal runaway is not immediately near a thermistor, significant time may pass before the thermistor registers a significant temperature rise. It turns out that voltage is a better way to detect that something has gone very, very wrong. And also, a BMS can't actually do much in this situation. It's too late to stop whatever caused thermal runaway. We can open the battery switch and disconnect the battery from the rest of the system, but that doesn't stop a fire inside the battery. And if we want to alert the user that the system has suffered a very major fault, voltage provides a faster warning that something is very, very wrong. Let's go back to the current measurement shunt to discuss why values of milliohms or fractions of milliohms are typical. We'll look at a specific example, the BMW i3. This 1,320 kilogram vehicle can accelerate to reach 62 miles per hour in 7.3 seconds. Let's calculate the corresponding battery current. Remember back to your physics class where you learned that power equals energy divided by time and is measured in Newton meters per second or joules per second. And also that kinetic energy is 1/2 mv squared. From some beginning electronics class, you may recall a different expression for power: voltage times current, measured in watts or joules. We'll use both these equations and set them equal. Now, let's plug in numbers. 1/2 mv squared with a 1,320 kilogram vehicle at 27.7 meters per second has 500,000 joules of energy. That 500,000 joules of energy came from the battery. 500,000 joules divided by 7.3 seconds is the power drawn from the battery while the vehicle is accelerating, and it is equal to the battery voltage of 352 volts times the battery current. Solve for current. 197 amps, assuming no losses and perfectly uniform acceleration. All that current flowed through the battery shunt. As that current flows through the shunt, our BMS measures the resulting voltage across the shunt. And because the shunt is a resistive element, some power is dissipated in the shunt. Let's calculate these two quantities. For a 1 milliohm shunt, with 197 amps, we'll see 197 millivolts across the shunt, which is a measurable voltage. That's good. But we'll also see nearly 39 watts of power dissipation in that shunt. That is a problem. The loss of energy is inefficient, but more importantly, that much heating in a single component is problematic. With 39 watts, that shunt will get hot. Metal has a temperature coefficient, so a hot shunt will have a different value than a room temperature shunt. So we'll get poor current measurement accuracy. Remember, we wanted a precision resistor for a precision measurement. Let's consider a 0.1 milliohm shunt. We still get a measurable voltage, 19.7 millivolts, and now a power dissipation that's much easier to manage. We had two discretionary measurement functions, board or chip temperatures and diagnostics. You could actually say that board or chip measurements are a diagnostic. We'll give a cursory glance at diagnostics now and dive deeper in a later lecture on safety and fault detection. Here are two BMS chip evaluation modules, the left one from Texas Instruments, the right one from Linear Technology, which is now part of Analog Devices. The intent is that you might buy one of these to evaluate the cell voltage measurement chips. While the board layout is not optimized for production, it implements the key functions that each BMS chip supports. Other than the connectors and slider switches, which are not production intent, the largest functional block are the cell balancing resistors. We can turn them on selectively to discharge selected cells. For various reasons, cells can become unbalanced, their voltages unequal. Cell balancing allows us to selectively discharge the highest cells to bring them into balance with the rest. Of everything you see on these boards, balancing probably dissipates the most heat. In some applications, the heat dissipation is enough that it can overheat the components on the board. If we have a large battery where we want large cell balancing currents, measuring temperature near the balancing resistors can be a good idea, so we can turn off balancing and allow the board to cool down if needed. We might also want to measure the BMS chip temperatures. Their accuracy can degrade when hot, and in some cases that's important. We might want to check whether our connectors are connected. It turns out that connectors are good at connecting, but they are also prone to disconnecting. Many BMS chips can apply a tiny current to the cell sense line. If there's a cell connected, nothing changes. If the connector is disconnected, the tiny current changes the voltage. BMS chips intended for automotive applications offer self-diagnostics. They might have a test mode that applies a known voltage to the ADC to verify that the ADC is measuring correctly. They might have a secondary voltage reference that we can compare against the primary reference to verify that they match. BMS chips tend to have a tiny bit of memory, and the automotive ones can check that the error correction codes match the data. An automotive BMS chip may implement tens of such diagnostic checks. Next, we'll talk about fault detection. Fault detection falls into two categories: system safety events, which are risky in themselves, and BMS faults, which indicate that our BMS has a problem. That is, we can't fully trust what the BMS is reporting or doing. When a system safety event occurs, we must take action. Our battery system is in an unsafe region of operation. When a BMS fault occurs, we cannot monitor some aspect of the battery, possibly like not having a BMS at all. But the fault is not unsafe in itself. Let's look at some examples. Overvoltage and overtemperature will permanently damage cells. Severe overvoltage or overtemperature can cause cells to go exothermic. Aged cells are more susceptible to exothermic reactions. Undervoltage can damage a cell and make it susceptible to going exothermic next time it is charged. If you have undervoltaged a cell, you should not charge it again. Pulling too much current out of a cell can also damage it. Quite often, though, overcurrent mitigations are about protecting the system outside the battery. Overcurrent often happens due to a short outside the battery. A sustained high current short can lead to fire or other significant damage outside the battery. I think you can see how all these faults require a fairly immediate response. Whether immediate is microseconds or milliseconds or seconds, we'll analyze that in a future lecture dedicated entirely to fault detection. Now let's look at some examples of BMS faults. A disconnected sense wire is a common one. Connectors connect, and sometimes they disconnect. A loose connector or broken wire is not dangerous in itself. It won't propagate to cause fire or other collateral damage. However, if we allow further charge or discharge, we cannot monitor to ensure that we avoid a system safety event. Many types of faults can cause bad data. A flipped memory bit, a damaged ADC, or electrostatic damage to a pin on the measurement chip are three examples of single-point faults that can lead to bad measurements. For each of these, a diagnostic is possible to determine that something is not right, to allow the BMS to raise a flag. Again, These are all harmless in themselves, but leave the BMS running blind or partly blind. A third example of a BMS fault is a problem with balancing. You could imagine a bad solder joint causing a balancing resistor to disconnect with the balancing circuit no longer connected to the cells. The battery can continue to operate with this fault for a long time, weeks or months. Imbalance in itself is not a safety issue. If one cell is at top of charge in 4.2 volts, while another is at 4 volts, we're sadly missing out on using the full capacity of those cells, but there's no safety concern. Now, let's review the key state estimation functions of a BMS. State of charge estimation aims to figure out how fully charged or discharged the battery is. This is useful for several reasons. The user can find it useful to know how long their battery-driven application will keep running. The control system may throttle back power to extend runtime, for example, reducing power drawn by an electric motor or powering down non-critical auxiliary loads. A charger needs to know state of charge and voltage so it can stop providing current when the battery is full. State of charge estimation algorithms rely on 3 of the measurements that we've discussed: cell voltages, cell temperature, and battery current. My wireless earbuds report their state of charge on a 5-point scale: full, 70%, 50%, please charge, or refuse to turn on. I suspect that internally a very simple BMS implements a very simple lookup table based on only the cell voltage. For this application, which is not safety critical, a replaceable consumer device, this low level of fidelity is enough. For larger batteries, where greater accuracy is valuable, we must implement something more sophisticated. A common approach is to use a cell model that captures the complexity of a cell's behavior with varying temperatures, current load, and aging. This model is informed by data, with the model parameters derived from the cell measurements taken across different temperatures and discharge rates. We will look deeper at this model in the lecture on cell behaviors. I'd like to give you the gist of how state of charge estimation works. When the battery is well rested, the cell voltage measurement closely approximates the open circuit voltage, or OCV. And from OCV and temperature, we can determine the state of charge in percent. But when current is flowing, or when current has been recently flowing, the cell terminal voltage, which is what we can measure, is messy. It differs from the open circuit voltage. Current, combined with the cell impedance, gives us a voltage drop. And cells have time constants. It takes a cell time to relax after a current pulse. But if we can measure current and time, we can just sum or integrate that current measurement to tell us the total amount of charge that we've pulled out of the battery or pushed into the battery. While the battery is operating, the current measurement is the key measurement contributing to state of charge estimation. The trouble with Coulomb counting is that any measurement offset error is accumulated. Say we have a 10 milliamp measurement error. After an hour, we will have a 10 milliamp hour error in our state of charge estimate. After 10 hours, we'll have a 100 milliamp hour error. After 100 hours, we'll have a 1 amp hour error. The integrated error just keeps growing, as you'd expect from integrating a constant. And thus, we use the voltage measurement to return to ground truth. Our voltage measurement is what eventually allows us to correct for the accumulating Coulomb counting error. However we implement this, state of charge estimation is a sensor fusion problem. We have data from multiple sensors, and we want to fuse them into a single state estimate. State of health estimation means adjusting the cell model parameters to reflect cell aging. As a cell ages due to calendar time passing, due to being stored at high temperature, or due to sourcing or sinking high currents, its behavior changes. Cell impedance increases, which means that when we pull large currents, we will see larger voltage drops. Also, cell capacity decreases, so the runtime of our application will decrease correspondingly. It is important for the BMS to estimate how much power it is okay to put into or pull out of the battery. For example, when the battery is cold, it cannot provide full current. It also has a higher impedance, so when we pull current out, we will see the voltage droop more than at room temperature. The BMS must communicate to the charger whether the battery is able to accept charge, and if so, then at what rate. The BMS must similarly communicate to its load, a motor or an inverter, at what rate it can extract energy. Now, we'll discuss the actions that a BMS can take. There are 3 actions, really. And we'll start with opening and closing the battery switch. A BMS controls a battery switch that can disconnect the battery from the rest of the system. This is important for a few reasons. When the system is off, disconnecting the battery is safer, especially for high voltage batteries that may have 400 volts or 800 volts at the terminals. For example, we don't want a mechanic servicing another part of the system to inadvertently short the battery with a metal tool when servicing another part of the system. Disconnecting the battery also reduces parasitic current draws. For example, if whatever is powered by the battery doesn't turn off completely, it can slowly drain the battery. The battery switch is also our last line of defense in case of certain faults. For example, a short outside the battery can pull a large current from the battery, and that current can damage the battery or the wires and connectors between them. The location of the short may get very hot, resulting in propagating damage. Opening the switch may need to be done quite fast. The switch is also the last line of defense if the charger or motor disobey BMS current limits. For example, when the battery is cold, the BMS should politely ask for only small currents. But if the motor or inverter disregards the polite request, the BMS should open the switch to prevent battery damage. Some battery systems may not need a switch. Let's consider when and why. The safety functions provided by a switch can be grouped into 2 categories: protecting people or systems outside the battery, and protecting the battery itself. If the battery is small enough and the system operation not critical, maybe we don't need those protections. For example, the battery in this remote-controlled paper airplane is low voltage and touch-safe for people. If a person or a metal tool inadvertently shorts across something powered by the battery, the consequences are mild. And as far as protecting the battery, the relative cost of the switches may outweigh the value of protecting a few batteries from being damaged. Let's look at the relative value of a switch in every system versus repairing a few systems. Imagine that our production run manufactures 100,000 airplanes, each incorporating a 10-cent protection switch. That's a $10,000 manufacturing cost. Consider a 0.1% field failure rate for problems that could be mitigated with a switch. We're looking at 100 airplanes where battery damage could be prevented by incorporating a switch. If the battery costs $4, that's a $400 warranty cost or user cost. It doesn't make sense to spend $10,000 to prevent $400 in damage. The choice of device to use for the switch depends on the details of the system. In small, low-current systems, MOSFET transistors can be a good choice. They are small and can be mounted on the same board as the rest of the BMS electronics. Because discrete FETs inherently incorporate a body diode, we actually need 2 FETs to block in both directions. We'll look at that in more detail in the next slide. The picture here shows back-to-back NFETs, but you could use PFETs. A second option is a relay. The nice thing about a relay is that when it is open, it is truly open. A relay is a mechanical device that creates a physical gap between 2 pieces of metal. It completely breaks the circuit. No leakage current when open. A key disadvantage is that relays typically tolerate fewer switching cycles than FETs, and that's common when you compare a mechanical versus an electronic solution. High current systems, such as electric cars, often implement a contactor, which is a high current relay. Electric vehicle contactors are carefully designed to open even when current is flowing, which turns out to be tricky, and we'll see a bit more in a couple slides. Here's what one contactor looks like. You can see two metal posts at the top, which would go to the battery and the system respectively. And you can see an actuated metal plate moving up and down to alternately connect and break the current path. To use MOSFETs to disconnect the battery from the rest of the system, we need to use two transistors in series because every FET incorporates a body diode. If we use only one FET oriented as shown, even when we open the FET, the body diode can still conduct. We can still drain the battery. Okay, that's no good, so let's flip the switch. Now, with the switch open, we can no longer discharge the battery, but we can still charge the battery. If you use only one FET, then the switch can block either charge or discharge, but not both. To disconnect the battery blocking both charge and discharge, back-to-back MOSFETs are the solution. When the FETs are open, and the body diodes point in opposite directions, we block current flow in both directions. The two topologies, common drain and common source, require slightly different controls. A FET is controlled by the gate source voltage, or VGS. In the common source arrangement, we can use a single gate control voltage for both FETs, since their sources are tied together. This is convenient. However, when the switches are open, the voltage between those two FETs is driven neither by the battery nor the system, and we must ensure that whatever drives the gates does so relative to this in-between node. The common drain arrangement requires a separate driver for each gate, with separate voltages. If you're curious about why FETs have a body diode, watch the supplemental video, What is a Body Diode? Now let's talk about contactors, specifically opening them. I told you that contactors are tricky to open when current is flowing. Let's talk about why. Imagine a hefty power supply, perhaps a 400-volt electric car battery. Imagine a hefty current load, perhaps 200 amps, because the vehicle is accelerating when a fault happens. Between the supply and the load is a contactor. What happens when this contactor abruptly opens? In the ideal circuit drawn here, the current abruptly stops. It's quite boring in the ideal world. The trouble is that in the real world, we have parasitic inductances. So when we open the switch, the current keeps flowing. This incoming current on the left and outgoing current on the right cause a large voltage across the switch, possibly larger than the battery or power supply voltage. What happens when you have a large voltage across an open switch, or worse, a barely open switch? A large voltage across a small air gap can cause an arc. This ionizes the air, reducing its resistance, and the electric current can continue to flow across the air gap. This may happen briefly, with the arc stopping once the switch opens wide enough. Even a brief arc can cause damage to the contact surface of the switch. Or, the arc may conduct until something else in the system breaks. Bad outcomes are possible. Let's watch an arc. The UT Center for Electromechanics created a setup with a 650-volt DC power supply, a 150-meter cable, a 175-amp load, and a switch consisting of carefully controlled electrodes which can separate at 1/10 of an inch per second. As the electrodes separate, an arc forms. Let's watch snippets of this video. Here it is at normal speed with normal lighting. Notice how at the end, the arc stops when the right electrode abruptly flies off to the right. You can follow the link to watch this in slow motion and also a recording through a welding mask. Let's review the purposes of the switch. The switch needs to isolate the battery when the system is off and to disconnect the battery when a fault occurs. This corresponds to three possible actions: closing the switch, which happens with zero current flowing because current doesn't flow when a switch is open. Opening the switch with zero current flowing, which is what we do when the system powers down in a controlled fashion, and opening the switch with current flowing, which happens when responding to a fault. The simplest architecture is a simple switch. Many switches aren't designed to open while current is flowing, or can only open with a small current. For small batteries and small systems where overcurrent protection isn't critical, this may suffice. For systems requiring overcurrent protection, we can upgrade our switch to a contactor, which is a relay designed to open while current is flowing. All contactors are limited to some maximum current at which they can open. We can select our contactor to break the maximum system current, but oftentimes a short-circuited battery may provide a current well beyond that. To protect against high currents, we add a series fuse. We split the protection function across two components. Note that a contactor can open repeatably, while a fuse creates a permanent open. A third possible architecture is a switch that cannot open under a current load, combined with a pyrofuse. A pyrofuse is an electronically controlled fuse which incorporates a pyrotechnic device. The electronic control allows very precise control of the current at which the device opens, and a small explosion results in a fast and consistent opening time. Traditional mechanical fuses open more quickly at high currents and more slowly at low currents. A weakness of this architecture is that we give up the ability to reversibly open the switch in case of a small yet undesired current. Let's take a closer look at fuses versus pyrofuses. A fuse contains a metal strip or wire that opens when the resistance of the element generates enough heat. Every fuse datasheet contains curves showing the opening time as a function of the current. For any given fuse, the opening time gets shorter with increasing current. Let's look at the curve for the 200 amp fuse. Here, I've labeled some of the opening times. This means that our application is okay for any length of time for any current below 200 amps. And the fuse will open for any combination of time and current to the right of the blue fuse curve. Consider the in-between. There is a range of currents for which the fuse will open only after the current has persisted long enough. This poses some design challenges. Though our system may be designed to withstand 200 amps, in some cases it may be subjected to higher currents for long enough to be concerned about collateral damage. Let's compare that to a pyrofuse designed for a similar maximum operating current. A pyrofuse is a more complex, more expensive device with a single spec for operating time. Upon receiving an electronic control signal, the pyrofuse activates an explosive device to rapidly and permanently open a gap between its two power terminals. That opening time is about an order of magnitude faster than the fastest opening times for a traditional fuse. Given that the control is electronic, we can design the controls to activate the pyrofuse at any current of our choosing. For example, we can choose to activate the pyrofuse at some current just above our 200 amp application maximum. We would analyze system noise and sensor error to select the margin between our maximum application current and our pyrofuse activation current, aiming to ensure that we never fire below 200 amps. A pyrofuse allows a smaller margin between our maximum normal operation current and the range of fault currents that trigger our safety device than what's possible with a traditional fuse. In this video, a circular hole in the side of the device allows us to see what a pyrotechnic device looks like blowing up. We talked at length about opening the battery switch. Now, let's talk about closing it. Consider a high-voltage battery connected to some system. Any system has some capacitance. Motors and inverters in particular tend to have large, explicitly designed-in capacitances to smooth their fast switching transients, on the order of millifarads. Let's consider the voltages on either side of the switch when the switch is open. On the left, we have the battery. In this example, let's say 400 volts. On the right, we have an unpowered system, so we expect 0 volts. If we simply close the switch, we'll see a very large inrush current. For example, if the big fat bus bars and connectors have a combined impedance of 1/10 of an ohm, we might see an initial current of 4,000 amps. Wowzers! For big systems like home energy storage and cars, this inrush current may be unacceptable. To mitigate this, we do what's called pre-charge. Before we close the battery switch, we pre-charge to equalize the voltages across the switch. The simplest way to do this is with 2 small switches and a resistor. When we close those 2 switches, we get a well-controlled current whose maximum is set by the value of the pre-charge resistor. Once the voltage on both sides is equal, we can close the main switch and open the pre-charge switches. A key challenge is time. You all hopefully have seen the equation I equals C dV dt. It's a prerequisite for this course. If we apply that to a 400-volt battery, 20 millifarad capacitance, and 2 ohm pre-charge resistance, we get a pre-charge time that's a noticeable fraction of a second. When the customer powers up the system, the best user experience is if that power-up time is negligible. 1/5 or 1/3 of a second is perceptible. There's a system engineering trade-off here between user experience and component lifetime, or cost, since we can design a more complex and faster pre-charge circuit. We also need to decide where to put the battery switch. We can put it on the top side, the bottom side, or both. What do you think is best? It depends on the application. In a car, typically the car will have a chassis ground that is separate from battery ground. This is for safety reasons. We'd like the system to tolerate single-point faults gracefully. If any part of the battery shorts to the vehicle chassis, whether it's cell 1 or cell 12 or cell 96, we don't want a problem. If the battery is isolated from the vehicle chassis, a single point short like this creates a single connection, and a single connection does not make a circuit. No current flows. We need to be very mindful of safety when working with potentially lethal voltages. Now, imagine an electric skateboard with a small 36-volt battery, a very different safety situation. Many would consider this a touch-safe voltage. Without a safety concern in mind, the only thing that the battery switch needs to do is ensure that we cannot inadvertently drain or charge the battery. And for that, simply breaking a circuit, a single switch suffices. Whether we put the switch on top or bottom is mostly a matter of which is easier to implement. Now, we'll discuss what a BMS should communicate with the rest of the system. We saw this diagram in the introductory lecture in the section on system architecture. Let's look at it again and list the key communications between the BMS and everything else. The BMS communicates with the charger to ensure that charging happens at an appropriate rate, including stopping when the cell voltages reach their recommended maximum. The BMS communicates with the motor to indicate when it may pull current and how much, including stopping when the battery is fully discharged. When the battery is too hot or too cold, the BMS should request heating or cooling, and likely that heater or cooler is located outside the battery. The BMS communicates with the main vehicle computer for a variety of reasons, such as reducing auxiliary power loads when the battery is low. Some BMS messages may be passed through the main vehicle computer for display to the user. For example, state of charge information may be reformatted and displayed as range remaining. Tesla is well known for sending significant vehicle data back to the manufacturer, and one might assume that some battery information may be included, and that other manufacturers may do the same. Let's write down what we saw in the previous slide. The BMS communicates allowable charge current. This prevents overvoltage and adjusts the charge rate to the present conditions. The BMS communicates allowable discharge current to the loads. This prevents undervoltage and again adjusts the rate to present conditions. The BMS communicates to the cooling and heating systems what the battery's thermal needs are. The BMS communicates to the main vehicle computer information which may consequently feed user warnings, or which may be sent back to the manufacturer if the application is connected to the internet or a cell network. The details will differ across applications. For example, for stationary energy storage, the system will have an inverter or a DC-DC converter in place of a motor. In small applications like electric skateboards, electric bicycles, and drones may not have thermal management systems. The last BMS function that we'll discuss is cell balancing. When we charge, ideally all cells in a battery pack reach top of charge together, like this. Ideally, if our maximum operating voltage is 4.2 volts per cell, all cells reach 4.2 volts simultaneously. In practice, for various reasons, cells can end up imbalanced, or in other words, cells can have different residual charge capacities. Residual charge capacity is how much capacity in amp hours can be put into a cell by charging, or how far from top of charge it is. We'll discuss causes of imbalance in the next slide. When we charge, since all series cells are charged with the same current, the cell with the lowest residual charge capacity will reach top of charge first. We stop charging when any cell is at its maximum voltage, so some cells end up not quite full. Balancing restores the more ideal situation. An ideal balancing algorithm is one that results in all cells having identical residual charge capacity. Passive balancing does this by selectively discharging cells as needed so that their residual charge capacities match, or, in other words, so each cell can take in the same number of amp hours before reaching top of charge. Let's talk about where imbalance comes from. First, we have self-discharge. All cells very slowly lose charge over time. If you put a cell on the shelf and check it a year later, you will find it at a lower state of charge than it started. If one cell self-discharges faster than another, they will become imbalanced. Self-discharge increases with temperature, so a temperature gradient across the battery pack will cause an imbalance in the cells. Unequal loads also cause imbalance. For example, if the BMS utilizes multiple voltage sensing chips to measure the cell voltages, and if those chips draw slightly different currents, that difference will imbalance the cells powering one chip relative to the cells powering the other chip. Some internal faults can cause high self-discharge in the affected cells, sometimes without propagating. For example, if you have a tiny defect in the separator, you might get a tiny local leakage between the two electrodes. Let's also talk about what doesn't cause. Capacity differences don't cause imbalance. I mention this because I've heard this idea, so I'd like to talk about where this idea comes from and what actually happens. Imagine two cells with unequal capacity. Here, I've drawn a factor of 2 capacity difference so we can see easily what happens. Let's start with both cells at 100% state of charge. As we discharge, the cell voltages deviate. When the smaller capacity cell is at 50%, the higher capacity cell is still at 75%. If all we look at is voltage, it appears we have an imbalance. But we don't. The residual charge capacities of these two cells are identical. When we charge again, the two cells reach top of charge concurrently. I told you that temperature gradients cause imbalance since self-discharge increases with temperature. It turns out self-discharge is also substantially higher at high state of charge than at low state of charge. This is kind of nice in that a nearly empty battery depletes itself more slowly than a fully charged battery. Here's a curve for one battery's self-discharge as a function of state of charge, and from the same source, an estimate of self-discharge with temperature. Let's do some math to get a sense of the size of currents we're talking about here. Say we have a 10 kilowatt-hour home energy storage battery, like a Tesla Powerwall. That's about 200 amp hours. Or an 80 kilowatt-hour electric car, also 200 amp hours. If a 2.4 amp hour cell self-discharges at 5 microamps at 80% state of charge, then a 200 amp hour battery will self-discharge at 417 microamps. Our worst case corner is at 100% state of charge and hot, say 45C, where we estimate the self-discharge to be about 7 milliamps. Take a moment to compare those numbers to other currents around the battery pack. A car may see a 1500 amp peak current for a couple seconds. A typical continuous current may be 200 amps. For a 200 amp hour battery, 200 amps is a 1C rate. Even when the application load is not present, we may have a computer or microcontroller running, or possibly other peripheral loads. Tesla Sentry mode uses the power-hungry autopilot computer, drawing perhaps 600 milliamps from the battery. Car headlights might pull 175 milliamp hours at the battery. A 1-watt microcontroller monitoring a home energy storage system might pull 20 milliamps from the 50-volt battery. Cell self-discharge is really quite small relative to these other application currents. Here, I plotted the rough numbers that we estimated on a logarithmic scale. We're looking at different orders of magnitude. As we discuss balancing, keep in mind that balancing corrects for currents that are thousands or a million times smaller than the application currents that the battery provides to whatever system it's powering. Those orders of magnitude are important to keep in mind when discussing passive versus active balancing. Passive balancing is what we saw before, drawing energy from the highest cells through a passive element, namely a resistor. The energy difference is dissipated as heat. This is a lossy method. Active balancing refers to using some circuit to shuttle charge between cells. The energy is not lost. It's moved from one cell or group of cells to another cell or group of cells. Sounds great, right? It turns out active balancing rarely makes sense. The value of the energy burned with passive balancing turns out to be small relative to the cost of implementing an active balancing circuit. Let's take a closer look anyway. For simplicity, consider a 4-cell battery pack. We need some way to move charge from any arbitrary cell to any other arbitrary cell. One possibility is switches. Maybe we could just connect the high cell to the low cell and let them equalize by putting them in parallel. Maybe we include some low-value resistors to limit the current. That's conceptually simple. Let's count how many switches we need. If we have n cells, we need n-1 high current switches. By high current, I mean high enough to carry the maximum application current. So if this is a 200 amp hour battery that may be discharged at 1C like a home energy storage battery, we need 200 amp switches. We also need 2N low current switches. These don't need to conduct the application current. They only conduct the balancing current. Consider looking around on the internet and estimating the cost of this solution for a stationary energy storage battery with 12 to 14 series cells, or an automotive battery with 100 series cells. Note also that this solution lets us balance one pair of cells at a time. To balance more than one pair of cells concurrently, we would need duplicate copies of the low current switch and resistor network. Also, we can only run balancing when the application is offline, since the high current switches interrupt the normal application's current flow. More frequently, I've seen proposals for active balancing using either capacitors or inductors as storage elements. This allows us to omit the high current switches, which substantially reduces the implementation cost. The implementation shown here would switch the purple cell to charge a capacitor or inductor, then open the purple switches, then close the orange switches to discharge the stored charge into the orange low cell. The switching frequency allows control of the current, just as in a switched capacitor circuit. Here are some further resources if you're interested in learning more about active balancing. I know I sounded a little negative about active balancing. I'm always interested to learn, though. If you work on a product in which active balancing makes sense, let me know. I'd love to learn and improve my slides. I have for you one last note on active balancing circuits. Let's think about how to control all those switches. Notice that these switches operate at different voltages. If we implement the switches as relays, the situation is conceptually simple since the control voltage is independent of the nodes being switched. However, not all relays have sufficient clearances internally to switch 50 volts or 400 volts. So, we need to be careful to pick an appropriate relay. Also, relays tend to have worse lifetime than solid-state devices. That is, in general, you can switch a mechanical switch fewer times than you can switch a transistor. FETs are a tempting option for these switches due to their longer lifetime. But the control gets tricky, since the control voltage of a FET is relative to its source. We need a different control circuit for each FET. We need what's called a level shifting circuit for every switch to level shift from some microcontroller's digital signal to whatever voltage range each switch needs. Only the bottom switch, the one connected to the constant 0-volt ground, can be controlled directly by the microcontroller or other ground reference digital circuit. Here's what a typical implementation of balancing may look like. We have resistors of value R-bal and switches. To balance a given cell, we close the corresponding switch and a current flows. The switches may be implemented in a single ASIC, which stands for Application-Specific Integrated Circuit, or colloquially a chip. You can find chips that integrate switches to monitor and balance 6 or 12 or 14 or 18 series cells. The balancing resistors are often implemented external to the chip, on a PCB or printed circuit board. These balancing resistors may dissipate more energy than anything else on the PCB, so in some designs, care must be taken with thermal management of the dissipated energy. It's tempting to design a high balance current so all balancing can be done while the battery is not in use. For example, say we want to design for that worst case 7 milliamp current and aim to spend only 1 hour per day balancing. We need a 168 milliamp current. This means that the two series balancing resistors will each dissipate about 1/3 of a watt. If you look at popular surface mount resistor power ratings, you note that a fairly large resistor is needed to dissipate that much power. Unfortunately, larger components tend to be a reliability headache. Since a component and the PCB have different coefficients of thermal expansion, as a board is thermally cycled over its life, every thermal cycle puts stress on the joints, solder joints. And those stresses are larger in the case of larger components. In practice, then, the designer must strike a balance between the trade-offs. One solution is to use a smaller balancing current, and in the small fraction of units that show a worst-case self-discharge, balancing may need to run concurrently with battery operation. Another solution is careful thermal design and implementing each balancing resistor as several series resistors. Another practical consideration is the impact of balancing on measurement. The wire harness has some resistance, consisting of connectors and the wires themselves. 1 ohm is a plausible connection resistance. BMS ASICs are carefully designed for very low input currents during measurement, to result in negligible voltage measurement error. But even if we design for a relatively small balancing current, small for a 200 amp battery pack that is, the balancing current causes a voltage drop across the sense wires, resulting in measurement error that is significant for state of charge estimation. This is one reason why it's tempting not to balance while the application is active. However, if the application does operate concurrently with balancing, an option is to interleave balancing and cell voltage measurements for state of charge estimation. As we will learn later, better accuracy is desired for state of charge estimation than for safety. An error of 10 or 20 or 30 millivolts may be tolerable within the safety architecture and problematic for state of charge estimation. Another option is a duplicate harness with 2 wires to each cell, one for balancing and the second for sensing. Cost is a concern for the dual harness solution. Let's summarize what we've learned about balancing. Balancing equalizes the cell's voltage or state of charge. Ideally, it equalizes the cell's residual charge capacity, or the amp hours remaining to top of charge, which is technically called top balancing. Some systems balance to another point on the curve. Balancing compensates for unequal discharge or leakage, including cell self-discharge internal to the cells and unequal loads external to the cells. Passive balancing is most common. Though it wastes energy, most sources of imbalance are orders of magnitude lower than typical application currents. Active balancing conserves energy, but requires more expensive and complex circuitry to implement. Balancing may impact cell voltage measurements to a degree problematic for good state of charge estimation, and we need to design to accommodate that. This completes the lecture on BMS functions in my Battery Management Systems course. If you liked what you saw and would like to see more, please let me know.